Hi everyone, welcome to the first remote instantiation of Nets 412. You're all muted right now, but I'm gonna briefly unmute you all so we can say hi to each other. So if you're doing something that's making embarrassing noises, stop, or physically block the microphone or something. Hey everybody.
Hey.
Hello.
Hello.
Hey, is everyone doing well in these interesting times? Don't all speak at once. So I'm going to begin the lecture in a moment, but I wanted to just begin, since this is our first class, back in the time of cholera, I wanted to take a moment just to have folks ask questions about how the class is going to run, or anything else. In general, maybe while I'm lecturing, the best way to ask questions will be in the chat. When I start lecturing, I'm going to mute everyone again. But before I do that, does anyone have any, like pressing questions they want to ask right away? Okay. So back on mute you go. I'm gonna allow people to unmute themselves. Actually, it's not such an enormous class that might not work. So I'm gonna mute everyone, but I'll allow you to unmute yourself. And if you have a question during the lecture, just unmute yourself and ask it. All right. Okay. So I was going to talk about the VCG mechanism. That's the next thing on our syllabus, and I will do that, but I'll do that next class. I figured this was a good opportunity to talk about epidemic models. So epidemic models, maybe you've heard something about them. They study how contagion spreads through networks. And often, as computer scientists, when we study these things, we are thinking about social contagion, like the adoption of some technology, or rumor spreading, things like that, and advertising, viral marketing. And actually, a big part of the computer science literature is studying how do you seed a contagion optimally to maximize its spread, which is not what we are interested in at the moment. But nevertheless, these models allow us to get some insight into the spread of other kinds of contagions as well. And I'm not going to talk about them today, but let me sort of point out, especially as some of you start to think about your final project, that there are game theoretic models of contagions. This is an algorithmic game theory class. I'm not going to talk about a game theoretic model today. I wanted to cover just sort of a basic model, but there are game theoretic models of contagion. You can imagine various action sets, for example, if it happens to be a contagion for which there's a vaccine available. You can imagine that there's the option, some costly option to get vaccinated, and you can study equilibria networks. People do this. You can imagine other action sets. And just to say a little bit about this, in these games, vaccination, which tends to prevent you from getting infected, tends to have positive network externalities, meaning that the good that you are doing by getting vaccinated, is not just to yourself. It makes it less likely that you will get sick, but it makes it less likely that the other people you're in contact with will get sick. And so there are positive network externalities that are not internalized, meaning you do not yourself experience the benefits of them. And what this tends to mean is that when you look at the Nash equilibria in these games, the price of anarchy can be large, meaning the Nash equilibria tend to result in under-vaccination compared to the socially optimal solution, because as a social planner, there are things that you would care about, like herd immunity, that aren't sort of directly experienced by particular individuals in the game. Okay. Now, of course, if we happen to unfortunately be in a situation where there is no vaccine, there's not much of a game to study, but we can still study the dynamics of how contagion spread and think carefully about the importance of reducing this quantity that many of you may have heard about in the last 2 weeks, called the R0. Okay, and we'll talk about that in a moment. So, so I want to talk about a mathematical formalism of contagion, right? This is ultimately a math class, and what I'm going to talk about today is a very simple model. So this is not, this is not the model that, like real epidemiologists would be using right now to try to make the most realistic predictions about what's going to happen in various places. This is a real epidemiological model, but the simplest one, right? And we're picking the simplest one just to sort of get a handle on what these models look like and how we can, like actually do some math on them. Okay, but here's how the simple model works. So the setting is defined by a graph. Okay, it's got vertices and edges. And the idea is that individuals, people, let's say, correspond to vertices in the graph, and the edges correspond to, let's say, social links along which contagion could possibly spread. Okay, so the edges correspond to, social interactions, the kinds of interactions you might have on a daily basis, like your fellow students, your coworkers, your family members, things like that. And in this simple SIR model, every vertex can be in one of 3 states, okay? I'll go through them, but as we talk about the dynamics of an epidemic in this model, what that will mean is the dynamics by which vertices transition between these 3 states. Okay, so it's the SIR model. S, I, and R each refer to one of the 3 states. Initially, the initial state for most people is that they are susceptible, S, they're in state S. And what this means is that they haven't yet become infected, and they don't have any immunity or anything to whatever the disease is, and so they are susceptible to it. They could become infected. Okay, now, if you are susceptible, you might transition into state I, meaning that you are not just infected, but infectious. This means that you have the disease, and if you are in state I, you are contagious, so you could affect others. Okay, and you'll stay in state I for some amount of time. We'll talk about that on the next slide. And then finally, after you have finished with state I, you move to state R. And depending on how grim a mood you're in, state R either stands for recovered or removed. But either way, if you're in state R, the infection has done whatever it's going to do, and you cannot become reinfected. Okay, so people transition from S to I to R. And so this is going to be a dynamic model, and the dynamics of contagion in the SIR model proceed as follows. Right, so initially, we need some seed set of infected people in order for anything to happen at all. And there's going to be some seed set of nodes in state I. Okay, the seed set start out as infected, and everyone else is susceptible. Everyone else is in state S. And there's a parameter of the model which says, okay, once you become infected, for how many steps do you remain infected? We're going to think about sort of a discrete time version of this model. So time will proceed in discrete steps. And if you become infected, you will remain infected for a number of steps that we'll call TI. And at every step, as time proceeds, if anyone who is in the infected state, in state I, can pass the contagion along to any of their neighbors who are in state S, who are still susceptible, and they'll do so probabilistically. So if you are in state I, then you pass the contagion on to your neighbors in state S, each one independently with probability P. Okay, so every day that you are in state I, for each of your susceptible neighbors, you flip a coin that has bias P, And if it comes up heads, then that neighbor also becomes infected and enters state I. Okay, and after you've been infected for TI steps, you enter state R, which sort of is removing you from this dynamics. You can't infect anyone anymore, and you also cannot become infected. Okay, so this is a simple model. This is sort of a model that imagines that after you're infected, you become immune. There are models that are for diseases for which people cannot develop immunity, in which case you can go back to step S afterwards. But we're going to work with this simple model. Right, so just to sort of get a feel for how the dynamics might play out in a particular graph, here's a very small graph. In this illustration, we'll denote the three states sort of graphically. The susceptible states are white. The infectious states are red with a black outline, and the recovered states are red but without a black outline. Okay, so here we're seeing some particular realization of the dynamic play out from frame A through frame D. Initially, Y and Z are infected. Note that the vertices that could become infected at the next step include X, T, and V. These are all the neighbors of the infected vertices, but they don't all become infected because infection is probabilistic. Only X and V do. Okay, and in this cartoon, the length of infection is only one time step. So as we transition from frame A to frame B, we see that Y and Z are no longer infected. They're now recovered, but X and V are. Okay, similarly, once X and V are infected, the set of vertices that could become infected next includes R and W. And again, since it's probabilistic, only R becomes infected. And then finally, in the final state, R fails to infect anyone else. The dynamics have burnt out. Everybody is either susceptible or recovered, and we can sort of figure out at this point how many people were infected. Okay, so before I sort of go on, let me take a moment just to pause and ask if the model makes sense. Does everyone sort of understand the model? Okay, so it looks like I have a question in the chat, but let me read this one out loud and answer it, but then other people should feel free to unmute themselves if they want to ask questions or just keep asking them in the chat. So I have a question that says, with probability P, does every neighbor become infected, or are the infections independent between neighbors? So they're independent. So the idea is, if you are infected, then what happens at one time step is, for each of your neighbors, I flip a coin, and with probability P, independently for each neighbor, they become infected. So it's not that you either infect everybody or nobody, you infect some people. Are there any other questions? All right, then let me go on. So a key quantity of interest, oh, I've got another question. What if a node has two infectious neighbors? Good question. So if the dynamics, sort of each of your infected neighbors has its own fair shot at infecting you, right? So each of them would independently flip a coin, and if either of those coins came up heads, you would get infected. So it's bad news for you if you have many infected neighbors. That makes it more likely that you will get infected because each of those neighbors might independently infect you. Good question. Any other questions? All right. So a key quantity of interest when we study the dynamics of an epidemic in the SIR model is this thing called the basic reproductive number, written R sub 0, which you've probably read about quite a bit in the popular press over the last few weeks. And this is sort of a simple quantity. It's the expected number of individuals that a randomly selected individual who is infectious will infect before they sort of are no longer infectious, before they go to state R. So it's sort of the expected number of new infections that any particular infectious person will themselves cause. And as we're going to see in sort of a simple model, this is a really important quantity in figuring out, whether the epidemic will blow up to, horrible proportions, or whether it will peter out. Okay, let me just. So, in full generality, right? Like, even though this is a simplified model, it's not like that simple, right? It's still kind of complicated to think about what's going to happen, because the model has a lot of parameters, right? Like, in general, in order to think about what's going to happen, okay, well, there's these sort of simple parameters of the model that maybe I could like hope to get a handle on, like Ti, the length that an infection persists, or P, the probability that if you are infected, you will go on to infect someone else. But the really complicated parameter is the graph topology, right? Which is, of course, really important in understanding how real epidemics spread, right? Like, there will presumably be sort of pockets of infection. There might be like bottlenecks in the graph. You might sort of build up herd immunity, which basically just means, sufficiently many people are in state R so that the infection dies out, but you might build that up, like locally in some parts of the graph and not in others. So in general, even this simplified model is, really too complicated to say anything really crisp in general. Although, of course, you can do simulations, and that is exactly how epidemiologists typically use models like this. They're not proving theorems. They're trying to design as sophisticated and robust models as they can, and then they're going to run simulations to see what happens. And of course, as I mentioned before, and just bringing it up again, as some of you think about your course projects, you can think about building games on top of this model by introducing, costs, like, costs for infection and actions, right? You could imagine that there's actions related to vaccination. You could imagine that there's actions related to changing the graph topology, right? Like, maybe if you hole up in your basement, you can really reduce your in degree, but that's that's costly for you. And so you can imagine on top of this model, writing down a game and trying to think about what the equilibrium predictions are. But what I want to do now is sort of take this model and study it on an especially simple graph topology, okay? And show, right, like the point of studying this in an especially simple graph topology is to get the setting simple enough so that we can actually prove a theorem. Okay, and then what I want to prove is something that has maybe sort of been internalized into your understanding over the last few weeks, but is something that is not a priori obvious, which is that there are sort of really sharp threshold effects. Okay, it can be that decreasing the basic reproductive number, R0, by even a tiny little bit can have enormous outsize effects. Okay, like infinitesimal changes in R0 can have really enormous effects in the size of the epidemic. Okay, so I'm going to transition into talking about the special case that we're gonna analyze and we're gonna prove something in. But before I do, let me just take another moment to pause and ask if there's any questions. remember, you can either ask questions on the chat or by unmuting yourself. Okay. So here's the special case that I want to study, and basically I want to restrict myself to the simplest possible case in which we can still ask an interesting question. All right, so we're gonna set the parameters as follows. Okay, we'll take the infection time to be 1, and most importantly, we're going to imagine that the graph is really, really simple. The graph will be an infinitely deep k-ary tree. Right, what does that mean? Well, it's a tree, and every vertex has exactly k children. Okay, so from every vertex has 1 parent and k children. Every child has exactly 1 parent, and so the out degree of every vertex is exactly k. There's an edge going to each of the children, and the graph is infinite. So this keeps going forever, this branching process. And initially, we're going to imagine that the root is the only vertex that's infected. Okay, so the infection can only move downwards in this tree, and we want to ask questions about how the basic reproductive number predicts how many people will be infected. Okay, so in this tree, remember, once we've fixed all of these things, there's really only 2 parameters that we can play with. There's k, right? There's the out degree of every vertex. How many children does every vertex have? And there's p. What's the probability that an infected vertex will go on to infect one of its neighbors, which in this case is always going to be one of its children? Okay, so in this model, right, in this sort of simplified tree model, the epidemic has to proceed in waves corresponding to these layers. Okay, right, because because the epidemic starts at the root, and vertices only stay infected for a single time step. So after you become infected, you become you go into state R. You become immune at the same time that you infect possibly some of your children. So it's impossible for the infection to move up the tree, right? Everyone above you will have been recovered already. And it can't skip a layer in the tree, right? Because infections can only move along edges. And so, at stage T, the only new people who can become infected are at level T in the graph, right? So the epidemic's gonna sort of look like a wave that propagates down the tree. And so what's this modeling? The idea is that here, each infected person is gonna go out and just meet k random people, right? These are sort of modeled as the children in the graph. So the thing that we're abstracting away from a more realistic network is that there's structure in the people you meet, right? Like you're probably gonna meet many of the same people as the other people in your household today, and in more normal times as your classmates and colleagues and such. In this model, we're sort of imagining instead that you're just going out and meeting k random other people, right? And so this infinite tree, what it's really approximating is just random interaction in an extremely large population, right? It's ignoring all of the sort of actual structure that's in a social network, and it's imagining that the random people you meet haven't yet been infected, right? So that's sort of why it's modeling what's going on in a very large population. But it's not a crazy model for what might happen at the very early stages of an epidemic before it's likely that you have sort of met other people who've already been infected. Looks like I've got a question. Let me read it out loud for everyone. Is it an accurate understanding that each time an infection occurs, it is like starting an entirely new and independent game rooted at that infected child. Yes, that is accurate, and in fact, that observation is going to be a key reason why this model is going to be analytically tractable. We'll see that in a moment, but the reason why we're going to be able to prove something in this model is because we can write down a recurrence relation that is exactly taking advantage of this observation that when I infect a child vertex, right, that's starting an entirely new epidemic in the subtree rooted at that child vertex that is entirely symmetric to the to the larger epidemic model, right? So every child is the root of their own tree, and we have sort of this fractal-like structure where every subtree is identical to the tree as a whole. So that's a good observation. Other questions? Okay, so just to sort of visualize again, like what might happen here, we start with an infection at the root. The infection propagates down the tree. Of course, it doesn't deterministically, the root doesn't deterministically infect all of its neighbors. It flips a coin and infects each of its children with probability p. Here we see the first two children were infected, not the last one. And then sort of recursively down each of these trees, each of these subtrees, the same dynamics continue potentially forever. Okay, it's an infinite tree. Okay. So in this model, it's actually quite easy to calculate the basic reproductive number. Remember, what is the basic reproductive number? It's the average number of new infections that a randomly chosen infected person can be expected to cause before they recover. And in general, again, this might be like a complicated quantity because it depends on what the graph structure looks like, near an infected person. This might be very different for different people. It depends on how many of your neighbors in the graph structure have already been infected and are therefore no longer susceptible. But because we're thinking about an infinite tree, all of those complications go away. And the basic reproductive number here is just p, right? The probability that you infect a random person times k, the number of neighbors, the number of susceptible neighbors that everyone has in this graph, the number of children. Okay, so these are also the only two parameters we have in this model, right? P and K. Right? It's an infinite k-ary tree. And so the basic reproductive number here is just P times K. It's the expected number of children that you will infect, because for each of your K children, you infect them with probability P. All right, does this make sense that the basic reproductive number here is just P times K? Okay, and so so we've got some model, and the question is, okay, can we now ask some question about the model that we can answer with math now that we've sufficiently simplified the model? And the question that I want to ask is whether a small change, maybe even an infinitesimally small change in the basic reproductive number, right, R naught, this thing that maybe we hope to affect by social distancing, can result in an enormous change in the course of the epidemic, right? Is it the case that if you change your behavior just a little bit, you'll only change the course of the epidemic a little bit, right? The kind of thing you would expect in a robust system that was not too sensitive to any of its parameters? Or might it be that tiny changes in behavior can result in, tiny local changes can result in massive global effects? And because we're studying an infinite graph here, we can sort of ask an especially extreme version of this question, right? Like what's a big change in an epidemic? Like ultimately the thing that we're measuring is how many people total are infected over the course of the epidemic. And so in a finite graph, we'd have to think to ourselves, okay, how do I define, a big epidemic versus a small epidemic? But in a finite graph, in an infinite graph, we can ask an extreme version of this question, right? Because it might be either that the infection at some point dies out entirely, right? At which point we have infected only a finite number of people, which is like a vanishingly small fraction of our countably infinite number of people. Or it might be that in this model, the epidemic continues forever and literally infects infinitely many people. And so the version of the question that I want to ask is, since we're studying an infinite tree, can an infinitesimally small change in R0, the basic reproductive number, change the number of infected people from finite to infinite? Okay, does the question make sense? Or is it sort of clear that because we're studying an infinite tree, that either of the two following possibilities can happen, right? Like it could be that the infection dies out, and in fact, right, like it could die out very early on, right? Like maybe the root just doesn't infect any of its children. Or it could die out at any other level. Or, right, like we might, we might be able to, the infection might grow large enough that it never dies out, right? Even though it has infinitely many opportunities for it to die out at each level, it might be that with positive probability, it never dies out because the number of infected people is sort of growing proportionately as well. Okay, and we want to ask whether we can say anything about the relationship between the basic reproductive number, R0, and which of these two possibilities we're likely to see. Right, so let's just sort of note a couple of obvious pieces of structure here, right? The only way that the infection can die out, right, is if there is some wave, some layer of the tree at which the contagion fails to infect anybody at the next level. Okay, right, because the infection proceeds sort of in waves down this infinite tree, well, first, if the infection is going to continue forever, it had better be that at every single layer, the infection, the epidemic successfully infects at least one person at the next level, the next layer down in the tree, right? And similarly, if the infection is going to infect only finitely many people, then it had better be that there's some last layer of the tree at which anybody is infected, and past that, nobody's been infected, right? It's got to be that there's some layer at which the infection just fails to pass down to the next level. If that doesn't happen, it infects infinitely many people because by definition, it will infect at least one person at each layer, and there are infinitely many layers. Okay. And so here's the theorem that we're going to prove. And the claim is that there's sort of this knife edge phenomenon. Like what happens really depends in an extremely sensitive way on which side of 1 the basic reproductive number is on. So in this model, if the basic reproductive number is less than or equal to 1, meaning that on average an infected person infects 1 or fewer of their children, then the claim is that with probability 1, the contagion dies out only after a finite number of waves, right? The chance that this contagion goes entirely out of control and infects everybody is 0. Okay. On the other hand, right, like if the basic reproductive number is even a little bit bigger than 1, then the claim is that with positive probability, the contagion will actually go on to infect infinitely many people, that it will never die out. Okay. So note, of course, that we cannot say, even when R naught is much bigger than 1, that with probability 1, it will infect infinitely many people. In fact, there's always like a decent chance that the infection, even an extremely infectious contagion, there's a like decent chance that it dies out early on, just because when there's not very many people who are infected, it's easy for the virus to get unlucky, right? Like suppose that I have 5 neighbors and it's an extremely contagious infection, like I infect each of them with probability 2/3. So I actually like expect to infect quite a few of them, right? 10/3. But there's some reasonable chance that I fail to infect any of them, right? With probability 1/3, I fail to infect each of my children, and so with probability 1/3 raised to the 5th power, I fail to infect any of them, which is some constant probability. Right? So even an infectious disease can get unlucky, and it's easier for it to get unlucky early on. It's sort of harder for it to get unlucky once it's really infected a lot of people. But that's why we can't say, even when the basic reproductive number is very high, that with probability 1, it will infect infinitely many people. The way that we can say that when the basic reproductive number is less than 1, that with probability 1, it will infect only finitely many people. Okay, but what we see in this sort of knife edge phenomenon is that right around sort of this threshold of 1, you go from having no chance at all of having a major epidemic of sort of, in this case, infecting infinitely many people, to having a positive probability of doing so. Okay, does the theorem, the statement of the theorem, make sense? The rest of the lecture is going to be about proving it. So this is a good time to ask questions if there's sort of remaining questions about either details of the model or like specifically what we're claiming about it before we sort of go on and try to prove it. Is there any questions about any of that before we go on? Okay. And a little bit of editorializing before we go and prove the theorem. So the message is obviously that it can be very important to reduce the basic reproductive number, and there's 2 ways to do that, right? Because in this model, the basic reproductive number is p times k, right? So if you want to reduce the basic reproductive number, there's 2 things you can do. You can try to reduce p, or you can try to reduce k. Right, so here, reducing p sort of corresponds to things like, washing your hands, using hand sanitizer, and Clorox wipes if you can get that on surfaces and stuff, right? This doesn't necessarily reduce the number of people you interact with, but it reduces the probability that an infection is transmitted along any of those links. Or you can reduce k, and this is sort of what corresponds to what we call social distancing these days, right? Like staying in your home, not coming back to Penn, having remote coursework, right? This isn't reducing the probability of transmission along a link. It's diminishing the number of links, right? And both of these are important because they reduce to exactly the same extent the basic reproductive number. And right, the other message is really that this is a threshold effect, right? You can have really big changes just by reducing the basic reproductive number by just a little bit, right? Which is a little bit counterintuitive, and the reason why these efforts to reduce the basic reproductive number are important even for people who are not themselves personally that worried, right? Because of course, if you reduce p by only a little bit, if you reduce your own out degree, your own k by only a little bit, and you're the only one who does that, then it has very little effect on whether you personally will get sick, right? These are sort of changes that unilaterally have very little effect on your own outcome. But what this theorem is sort of pointing at is that they can have enormous positive externalities, right? That even if we make these sort of teeny tiny personal changes that individually have little effect on your own outcome, it can really drastically change the spread of an epidemic. Okay, so that's your little social lesson in 412. So let's prove the theorem. So first, I just want to set up some notation so that we can talk about the things that we need to talk about in a sufficiently rigorous way. So, we want to talk about the probability that the infection infects infinitely many people compared to the probability that it affects only finitely many people. And remember that we can sort of equivalently talk about whether the infection burns out after only a finite number of levels in this tree, or whether it continues going for an infinite number of levels, whether it continues going forever. So rather than asking the question directly about the number of people it infects, we can ask the question about, the sort of equivalent question for our purposes, about how far down the tree the infection will proceed before it burns out. Okay? And for a level n, let's just write q of n to denote the probability that the epidemic actually continues for at least n rounds, which just means that, right, q of n is the probability that there's at least one person at level n of the tree who ends up getting infected. Okay, and this is not the probability that it continues for exactly n rounds, right? It's not asking for the probability that the infection reaches level n and then stops there. It's just the probability that the infection gets to level n and possibly further, right? So we can talk about q of 1, q of 2, q of 3, and so on, and this will be a decreasing sequence of numbers, right? Or at least a non-increasing sequence of numbers, because if you get to level 2, that in particular implies that you must have gotten to level 1 as well. And in particular, like, we will be interested in the limit of this sequence as n, the level, goes to infinity, right? Because we want to know what is the probability that the infection continues forever, not just to level 5 or level 6 or level 1,000,000 or level 1,000,000,000, but forever. Right, so this is a decreasing sequence of numbers between 0 and 1, so it has a limit, and let's just denote that limit, the limit of q of n as n goes to infinity, by q star. Okay, this is the probability that the epidemic continues forever. And just to sort of rephrase the thing that we want to show, the thing that we want to prove, what we're interested in is whether q star is 0 or not. Right, if q star is 0, if the limit as the level goes to infinity, that the infection, that the probability that the infection reaches level n is 0, that means that with probability 1, the infection will die out at some finite level, and therefore will have infected only finitely many people. If, on the other hand, this limit is some positive number, like 0.5, 0.2, 0.01, that means that, although of course the infection might have gotten lucky early on and sort of burned out, there's some positive probability that this actually goes on to infect infinitely many people. Of course, in that case, the expected number of people that are infected would also be infinite. Okay, and so the theorem that we want to prove, just sort of rephrased in our new notation, is that if the basic reproductive number is less than or equal to 1, then this limiting probability, Q star, had better be 0. And if, on the other hand, the basic reproductive number is bigger than 1, then what we're going to show is that this limiting probability Q star is strictly positive. Okay, we're not going to say exactly what it is, but we'll just say that whatever it is, it's strictly positive. It's bigger than 0, which corresponds to saying that with some positive probability, infinitely many people are infected. Okay, so does this make sense? All we've done here is restated sort of in new notation with some new conceptual underpinnings, the theorem that we want to prove. We haven't done any proving yet, but we're going to be thinking about these Qn quantities now, and so I want to make sure that everyone's on the same page. So if you have any questions about either what Qn is, what Q star is, or why this thing that we want to show is equivalent to the theorem we said we were going to prove, this is a good time to ask them. Okay. So, so let's prove it, right? There's two parts of the theorem. There's the part of the theorem that applies when the basic reproductive number is bigger than 1, and there's the part of the theorem that applies when the basic reproductive number is less than or equal to 1. We'll start by proving the version that applies when the basic reproductive number is bigger than 1, meaning we're going to prove that when R naught is bigger than 1, with positive probability, infinitely many people are infected. But sort of the machinery we're going to build up here, it's actually going to be the same machinery that we use to prove the other direction of the theorem. And so once we've proven sort of the first half of the theorem, the second half of the theorem will follow very easily. And the sort of basic observation that's going to drive the whole analysis is this observation that was made earlier, that there's really this sort of self-symmetry in a tree, right? Like if I ask about what the epidemic looks like sort of in the whole graph starting from the root, this is really the same question as what happens in the subtree of one of my children, right? Does the epidemic continue forever or not, conditional on that child being infected? Okay, and that's the structure that we're going to take advantage of to sort of write down recursively some expression for these variables Qn that we care about. So consider the following event. We'll call it star. That the root infects one of its children, J, okay? And then, after having infected J, that the infection proceeds down at least n-1 rounds in J's subtree. Okay, so here's a little picture to sort of get a feel for this compound event, right? So this event, first of all, is defined with respect to a particular child of the root. We're calling the child J. And the event occurs if two things happen in sequence. Okay, first, child J has to be infected from the root. And then the infection starting from J has to proceed down an additional n-1 levels down its subtree. Okay? And here's where we're gonna use this sort of symmetry, right? What's the probability that this event star occurs? Well, it's a compound event, right? Two things have to happen in sequence. The first is that child J has to get infected, right? That happens with probability P. And the second thing that needs to happen is that starting at node J, the infection has to proceed down for an additional n-1 levels. But remember, sort of the subtree rooted at J is identical to the original tree. It's just an infinite k-ary tree. And so the probability that starting at J, the infection proceeds for n-1, for at least n-1 levels, is exactly the same as the probability that the infection starting at the root proceeds for n-1 levels. And so we don't know what that is yet, but we have a name for it. It's q of n-1. It's q sub n-1, right? That was just the notation that we gave for the probability that an infection starting at a root proceeds down for n-1 levels. And so this event star, we don't know what its probability is explicitly, but we have notation to write down its probability, right? It's exactly p times q of n-1, because two things have to happen in sequence. First, node J has to be infected, and then, right, that happens with probability p, and then the infection has to proceed down an infinite k-ary tree for at least n-1 levels. And that's exactly, the probability of that event is exactly what we've been calling q sub n-1. Okay, so we can ask, right, like, what's the probability that the infection proceeds down starting at the root for n levels, right? Like ideally, we would like to, if we're trying to get some recursive definition of q of n, we would like to be able to write q of n in terms of q of n-1, right? We'd like to be able to write the probability that the infection proceeds for n levels as a function of the probability that it proceeds for n-1 levels. And it's going to be easier to think about the sort of complement of that event, right? What's the probability, 1 minus q of n, that the infection fails to proceed for n levels, right? Well, if the infection proceeds for n levels, it must be that sort of event star happened for at least one of the children j of the root, right? If the infection proceeds for n levels, that means that the infection started through some child j of the root and then proceeded for n-1 additional levels. So the only way that the infection can fail to proceed for n levels is if event star fails to occur simultaneously for all of the children j of the root, right? And so that's a quantity we can write down in terms of the notation we've already introduced, right? Like the probability that event star occurs for any particular child j, we've already established, is p times q of n-1. And so the probability that event star fails to occur for a particular child j is just 1 minus that, 1 minus p times q of n-1. And remember, in this model, each of the infections is independent, right? Like whether node j is infected is entirely independent of whether some sibling node j prime is infected. And so in order for this event star to fail to occur simultaneously for every child j, right, it has to fail to occur independently for each child. And the probability of that occurring is simply the probability that the event fails for one of the children, 1 minus p times q of n-1 raised to the kth power, right? Because these events are all independent. And so, this wasn't quite yet what we wanted. We didn't get explicitly a formula for q of n, the probability that the infection does proceed for n levels. We got a formula for 1 minus q of n, the probability that the infection fails to proceed for at least n levels. But of course, we can solve for q of n and get what we want, which is some slightly complicated recursive formula for the probability that the infection proceeds for n levels, right? It is 1 minus p times q of n minus 1 raised to the kth power. The probability that the infection proceeds for n levels is 1 minus the probability that the infection fails to proceed for n minus 1 levels, conditioned on node j being infected simultaneously for all children j. Okay. So, we don't have like a numeric expression for q of n, this quantity that we're interested in, right? So we can't like easily evaluate what this thing is except by sort of brute force calculation. But maybe, right, the hope is that we can use this recursive formulation in which we've written q of n as a function of q of n minus 1 to somehow study the limiting behavior. Because remember, ultimately what we're interested in is the limit of this quantity q of n as n goes to infinity. Okay, so that's what we're going to do, but this was sort of a dense slide notationally, so let me pause again to ask if there's any questions about any of this. Okay. So let's try to think about what we can learn from this recursive formulation. And it's going to be helpful to think about this function f of x, which should look really similar to the recursion we wrote down on the last slide, right? Let's define this function f of x to just be 1 minus p times x raised to the kth power. Okay, this is exactly the expression we derived on the last slide, except that instead of writing q of n, I've written f of x, and instead of writing q of n minus 1, I've written x. Okay, but this is the function such that we can write the recursion that we derived on the last slide as follows. Q of n is just f of q of n minus 1. Okay? And so the probability that the infection reaches the first level, or the second level, or the third level, or the fourth level, and so on, all of these probabilities can be expressed as iterations of this function f, right? Like, the probability that the infection reaches level 0, the root, well, that's 1, right? Like, by assumption, the root starts infected. And so what's q of 1? Well, by definition, q of 1 is just f of q of 0. So it's just f of 1, right? What's q of 2? Well, q of 2 is just f of q of 1. So it's just f of 1, right? Q of 3 is f of 1, right? As we go further down the tree, the way our recursion tells us to derive the probability that the infection reaches each successive level of the tree is just by iteratively applying this function f over and over again. Okay, and so the thing that we need to do, right, because we want to study the limit of these quantities q of n as n goes to infinity, we need to study the limit of the sequence, right? The limit of the sequence that we get as we repeatedly apply f, as we iterate f over and over again. Okay, so we've got some like clean little math problem now, right? We've got this function f. It looks like something, and we want to figure out what happens if we iterate this function in the limit, forever. And so why don't we start by trying to figure out what f looks like? Why don't we plot f? And of course, we can't do that directly, right? We don't have like a closed form. Well, I guess we do have a closed form for f, but let's figure out with, in a lazy way what f, what some properties of f must be, sort of what it looks like in a cartoon. And I claim it looks like this. Okay, so we're seeing here, like a two-dimensional plot. There's an x-axis and a y-axis. There's two functions plotted in the range of x from 0 to 1 and the range of y from 0 to 1. And the function in blue is just the identity function. It's just the line corresponding to y equals x. So it's just the diagonal. And my claim is that this function f, whatever it looks kind of like this black line. Or the function f is actually underspecified right now because we haven't said what p is. But my claim is that whatever p is, so long as it's a number between, strictly between 0 and 1, the function f looks like this black line. Okay, and what do I mean by that exactly? Well, we know that the function evaluated at 0, no matter what p is, has to be 0. Right? If we plug in 0 for x, then the function value f of x reduces to, f of 0 reduces to 1 minus 1, so it's 0. Okay, so we know that the blue line and the black line have to meet at the origin. They're both, they both take value 0 when x is 0. Okay. What about when we plug in value 1 into the function? Right, when we plug x is 1 into the function, then the function just gives us the value 1 minus p to the k. And so long as p is some, non-zero number, some number strictly between 0 and 1, then 1 minus p to the k is going to be some positive number. And so 1 minus p to the k is going to be strictly less than 1. Okay, so we know that the black line and the blue line meet at the origin. And we also know that the black line, the plot of this function f has to be strictly below the blue line, strictly below the diagonal by the time we get all the way out to 1, right? Because the diagonal is just plotting y equals x, right? At, the blue line takes y value 1 when x is 1, but the black line we're observing takes value strictly less than 1 at that point. Okay, so we've sort of established the correctness of two parts of this picture, that the blue line meets the black line at the origin, and that it is strictly, the black line is strictly below the blue line at x equals 1. And, this is a polynomial, so we can pretty easily take the derivative, right? Here's the derivative of the function f, and we can note a couple of things about it, right? So first of all, if we write the derivative of the function f, we get just k times p times 1 minus p times x to the k minus 1. Okay, this is a function of x. And note two things. So first of all, since p is a number between 0 and 1, and here we're letting x range from 0 to 1, this function is always positive. Right, like it never becomes negative because p times x is always less than 1 and k times p is positive. Okay, so the derivative is always positive, which means this function is always increasing. But the derivative is also, the derivative itself is also decreasing in x, right? As we increase x, that means that the thing that we are multiplying k times p by is going down. Okay, so the derivative is decreasing but positive, and so that means that this function f is concave. Okay, which justifies another aspect of this picture I've drawn. And then finally, if we look at the derivative of this function at 0, okay, if we look at our expression for the derivative when x is 0, right? Well, it evaluates exactly to k times p, right? Because it's k times p times 1. And so the derivative at 0 is k times p. Remember, that's just the basic reproductive number. And we're assuming in this half of the proof that the basic reproductive number is bigger than 1. Okay, so what that means is that this function starts out increasing faster than the blue diagonal line. Okay, which finally justifies the sort of last important aspect of this picture, right? That the black line, our plot of f of x, starts at 0. And then for part of its trajectory, it's above the blue line because the derivative starts bigger than 1. And it ends up below the blue line because f of 1 is less than 1. And it's concave, so it never crosses the blue line, again, right? There's going to be like this single crossing property where the black line will start above the blue line, and then at some point it will cross it and end below the blue line. And there's this sort of single crossing, right? So these properties establish sort of the important part of this picture, which is that our plot of f of x, this black line, it's going to intersect the blue diagonal at some unique point x star that is strictly greater than 0. Okay, so this is sort of the key property of f that we're going to use. So a good time to ask again if there are any questions about this. This is the thing to understand. The rest is going to be sort of straightforward given this. Questions about this? Okay. So remember, we're interested in what happens when we start at 1 and then we iterate this function f, right? What happens when we look at the sequence 1, f of 1, f of f of 1, f of f of f of 1, and so on. Well, it turns out that it's sort of easy to visualize this process of function iteration in our little plot, right? Like we start at 1. Okay, let's sort of think about what happens on the x-axis as we start at 1 and then iterate the function. So we'll start at x equals 1. We can think about starting at x equals 1, y equals 1 if we want. So we start at the top of the blue line. Okay. Well, what does it mean to apply the function f to some x value if we're sitting on the blue line? Well, it means to sort of go straight down from the blue line to the black line, right? Because if our x value, if we're on the blue line, right, the way we get our y value to equal f of x is simply to move down to the black line, because the black line is plotting for us exactly the value at y equals f of x. Okay. And then if we want to do another iterate, then we can move horizontally again from the black line to the blue line. Okay, this is just setting our x value equal to our y value when we do that, because the blue line is just the identity y equals x. And then move straight down again to the black line, right? Because once again, that's applying one more iteration, because the black line is telling us exactly the value y equals f of x. Okay, and so the process of iteratively applying this function f, you can sort of visualize it as following this zigzag path, always starting at a point on the blue line, moving vertically down the plot until you get to the black line, right? And then moving horizontally until you get back to the blue line. That's one iteration. And you can continue that to iterate this, this function application. And note that during this process, right, our trajectory is always below the blue line, and it's always above the black line. okay? So it can't go through, it can't pass through any crossing point of these functions. And so it must be that the sort of iterated application of this function f converges to the unique fixed point x star greater than 0 that we established existed on the last slide, such that f of x star equals x star, this sort of crossing point between the blue line and the black line. Okay? And, right, like, you know, we're always making progress towards that point, and we can't pass it because that's a fixed point, right? F of x star equals x star. And so in this case, it must be that the limit as n goes to infinity of q of n, right? This limiting point when we iteratively apply f infinitely many times converges to some value q star equal to this point x star that we established must exist that's strictly greater than 0. Okay, so this establishes that when the basic reproductive number is strictly bigger than 1, then with some positive probability, the infection never dies out. So how about the other case? How about when, you know, what's different? What's different when the basic reproductive number is 1 or smaller? So, you know, we can draw the same plot again and ask ourselves, okay, well, you know, like, how does the picture change when r star is, when r 0 is less than 1? And a bunch of things stay the same, right? Like f of 0 is still 0, so the blue line and the black line meet at the origin. F of 1 is still less than 1, right? The derivative of the function is still decreasing but positive, so the function is still concave. But the big difference, right, is that if we look at the derivative of the function evaluated at 0, remember this was exactly p times k, this was exactly the basic reproductive number. Well, this is less than or equal to 1 when the basic reproductive number is less than or equal to 1. And the derivative is strictly less than 1, right? Strictly less than 1 when evaluated at any epsilon bigger than 1, sorry, bigger than 0. And so the picture looks exactly the same, except now the blue line and the black line intersect at only 1 point instead of at 2 points. Okay, they still intersect at 0, but there's no longer any crossing point. The black line is now always below the blue line. Okay, and so we can think about this function iteration in exactly the same way as sort of mapping out this trajectory that's always sort of you know, ping-ponging back and forth between the blue line and the black line. And the trajectory always stays strictly below the blue line and always strictly above the black line. And it, again, sort of inevitably converges to a fixed point. But now the only fixed point is at 0. Right, so now the convergence has to be to the unique fixed point, which is at 0. And so what we see is that if the basic reproductive number is even just, you know, a tiny bit smaller than 1 plus epsilon, which would have been enough to have it infect infinitely many people, then we get that with certainty the infection will burn itself out and infect only finitely many people. All right, so that's the theorem. Let me end the class now. So, you know, feel free to sign off, and, you know, we'll get back to real algorithmic game theory next class. We'll learn about the VCG mechanism and all of that good stuff that you'll need to complete the next problem set, which is, by the way, out today. But in the meantime, you know, wash your hands and stay inside to reduce the basic reproductive number. And I'll hang around on the line, you know, for a little bit longer for anyone who wants to ask questions, either about the material or about